Hello and a very good evening. So you're back with me Supriya Singhal on this course for UPSC CSC and BSc MSc for mathematics, and today we are covering modern algebra in continuation with the previous few lessons. So we are covering groups theory in modern algebra, and I've already explained you just a quick revision for like a minute basically. So we've already understood how to define a set to be a group. Then we told you some group properties like 5 properties: non-emptiness, closure, associativity, identity, inverse. Then we also discussed how do you define a group to be abelian or not. Then we discussed some finite sets problem and infinite set problems, and for finite sets we make something called a Cayley's table or composition table. Then we moved forward towards the properties of group. There were 7 properties of groups. First of all, uniqueness of identity, then uniqueness of inverse. Then it was about AB whole square was not equals to A square B square. Then it was about AB whole inverse was not equals to A inverse B inverse. Then it was about A inverse ka whole inverse is equals to A itself. And then it was about solvability, basically equation solving, like Ax equals to B type, and then you get X equals to A inverse B, and which was also unique. So for uniqueness, I already told you that whenever you have to prove uniqueness, you always prove it by contradiction. So you take two values and then in the end you prove them to be equal. Okay, so we are already done with this much, and then we started with something called as semigroups, and I told you it is not subgroups. So please remember, semigroups are not subgroups. So semigroup means basically a set which is satisfying only two properties of a group. Okay, so it is not a group. It is satisfying only two properties of closure and associativity. Okay, so the sets like I told you, like natural numbers with respect to addition, whole numbers with respect to addition, or even for that matter real numbers with respect to multiplication, are all semigroups but not groups. So hence all the groups are semigroups, but vice versa is not true. Okay, so we've already done till here in the previous class, and today I'll explain you how to basically under what conditions a semigroup becomes a group. Okay, so how do you do it? So for this, basically, if a semigroup is said to be satisfying left identity and left inverse, or right identity and right inverse, then we say that the semigroup becomes a group. Okay, listen to my words very carefully. I am saying a semigroup is there. That means it's already satisfying closure and associativity. So the remaining two properties that need to be satisfied for it to become a group are identity and inverse. So I am saying, instead of satisfying both left and right, that is left identity and right identity, and left inverse and right inverse, I am saying if a semigroup satisfies either one of it, that is left identity, left inverse, or right identity, right inverse, then it's a group. Okay, so how will you make it a group basically? So how will you prove it? If you are able to prove from left identity that you can prove it to be a right identity is also true, and if from left inverse, if you start from left inverse and you're able to prove that, you can also prove right inverse. Okay, so that's how you will say a semigroup becomes a group. Okay, so okay, so now just for explanation, what do you mean by right identity, right? So right identity just means that your identity element is coming on the right, as I told you before also. Okay, so left means, so like inverse, left inverse means that inverse element is coming on the left. Okay, right inverse means that inverse element is coming on the right. So if I'm writing right identity, that means identity element is coming on the right. Okay, so always it's the suffix that we're talking about. That means like right identity, left identity. So it's the identity element that decides whether it's right or left. Okay, so now you move on. So right identity means AA is equals to A, and similarly right inverse means AA inverse equals to E. Just a minute. Yeah. So how do you show it? So basically here what we are doing is, we are given that there is a semigroup, we are given that it is satisfying right identity and right inverse, and we have to show that it is a group. That means the only two properties that you need to show is left identity and left inverse. Okay, that is, we have to show that EA is equals to A and A inverse A is also equals to E. Okay, it's very simple. And how will you show it is all the more simple. So I mean, why don't you guys try it on your own? If you're not, then I'll explain it to you, because this has never been asked in the exam. But if I'll just like give you an overview, and still if you're not able to understand it, we can take this up in the what do you say, doubt session or doubt solving module basically, right? So how do you see, always these kind of questions, whenever you're doing, just remember that whatever you have to show, now you start from left hand side and prove it to be equal to right hand side, because there is no other way you can prove this. So you start with something called as EA, and then you just by through manipulations and through solving steps, you just show it finally to be equals to A. Okay, and I'll just show you for an example. Okay, so here the only catch was that you have to solve inverse first and then identity, because what is happening in identity, if you can see here, Just look at where my cursor is pointing. So I have written EA. So E you can be writing it as AA inverse because right identity is satisfied. Right inverse and right identity is satisfied. Hence E can be written as A into A inverse, and then this into A. And now by associativity, we know because semigroups also satisfy associativity, hence we can change the brackets. So they become basically A into A inverse A. But you know, now this is basically left. This is left inverse. So once if you prove that left inverse is equals to E, then you're sorted with this one, because then ultimately we'll get this equals to A and this will become A. So this again only, so this property identity can be solved only with the help of inverse. Okay, so first in this question we'll solve inverse. Just remember this much, that's it. That's the only catch here, because in the exam or in anything when you're solving also, you should not get stuck. So you should know how to basically come out of all these little what do you say, loopholes. Okay, so first we'll start proving with the inverse. Okay, so how will we do it? So we have written A as equals to A into E because right identity is satisfied. Okay, and now I am saying, just listen to me carefully. Okay, I am saying if there's an element A in the set G, then obviously there is an inverse of A also. Okay, then there is an element called A inverse, and now A inverse will also have some another element as its inverse called A double dash. So that is the whole crux. So now what I've done is A is equals to AE. Okay, an identity element can also be written as A inverse into A double dash. Why? Because A double dash was the inverse of A, and we know that the right inverse is satisfied. Hence, A inverse into A double dash. And now change the brackets. Now AA inverse is the right inverse. So this becomes E and this becomes E into A double dash. Okay, now just stop here and then go to A inverse A, which is left inverse property that we have to prove. Take A inverse A and write A as EA double dash. Okay, and now A inverse into E is right identity. So this will become A inverse A double dash, and we already know that this is nothing but E. So hence we are able to prove left inverse. And now we have, using that, we'll show that this is a left identity. Okay, I've explained you also now, so there is no need. But still, if you are having any doubt, just let me know. But remember, you have to solve first for what? You solve first for inverse and then go for identity. And secondly, you have to take A inverse, or A dash and A double dash, where A dash is the A inverse of A and A double dash is the inverse of A dash. Okay, that's the only catch here. Now, these are some random questions that we are starting. And these are pretty easy questions, and this is actually I think I've encountered it in one of the UPSC exams. So do check it out. So basically, it's about to show that a group G, which with binary operation means that closure property is satisfied. Okay, and given that A and B are two elements from the G, and their linear equations AX equals to B and Y equals to B have unique solutions X and Y and G. So basically, what do we have to show here? Just read the question. We have to show first of all not only that these equations have a solution, but also that they are unique. Okay, so always bifurcate the question. So the question has two parts. It's not just, it does not have one part. You will not get marks if you just solve one part. Okay, so you have to solve two parts of it. First is saying that there is a linear equation. There are two linear equations and you have to show that they have a solution. And the second part is, once you find the solution, you just have to show that the solution is unique, that there exists only one and one solution of X and Y. Okay, so how do we solve for part one? That I already showed you on solvability laws, right? So AX equals to B, and A and B are all the elements in the G, and G is given to be a group. Hence, A inverse also exists and B inverse also exists. So pre-multiplying both sides by A inverse, so hence you get X as A inverse B, and similarly here you post multiply by A inverse, so you get Y as B A inverse. Okay, see here. So this is post multiplying and this is pre multiplying. There's a huge difference between pre multiplying and post multiplying. Do not make this mistake of writing post multiplication instead of pre multiplication. You'll get 0 marks straight away. There is like no point of checking the answer, from the step that you have committed this mistake. You'll get straight away 0 from 15, 10, 20. I don't know how many marks it is for. Okay. So, and second part was about showing uniqueness. I told you like this, what do I say, mantra basically of how do you show uniqueness by assuming that there are two solutions and then proving them to be equal. So here I assume that there is x1 and x2, there are two solutions. And if there are two solutions, that means that they are satisfying this equation that ax1 is also equals to b and ax2 is also equals to b. Okay. And then from there, what will happen is, now B is a unique element, right? B cannot be like more than one B in the set. So they say, therefore, AX1 is equals to AX2. And we know that in a group, what happens? Left cancellation laws apply. Hence, X1 equals to X2. Hence, we are done. So it's very easy. So first you show the solvability and then you basically go for uniqueness. Now, second question. Second question is proving that you have to prove that the group is abelian if and only if your AB inverse is equals to A inverse, B inverse for every A and B that belongs to G. Now, what is the trickiest part in this question? That IFF that you can see here. IFF means if and only if. Okay, that's a short form of writing if and only if as IFF. So now this means that question has two parts. Okay, so this is the trickiest part. The first part is assuming that the group is abelian, you have to show this property. And the second part is the reverse. Assuming that this property is satisfied, you have to show that the group is abelian. Okay, whenever there is IFF, which is if and only if, you have to show reverse. Like you have to show the straightforward and its reverse. Okay, so here, first see, two parts can you see here? So part one is about given that the inverse is this, you have to prove that the group is abelian, and the second part is about proving that there is this equation is satisfied given the group is abelian. Okay, so we have to solve each part differently, and do solve it differently, because what happens is even if you make mistake in one part, or like at least you get some marks. I mean, step marks are given in maths. That's the beauty about it, right? So basically now part one is about given that your AB whole inverse is A inverse B inverse, you have to show that the group is abelian. Okay, so that is. Now just bifurcate the question in mathematical formula. So group is abelian means what? That if you take any two random elements A and B from the set, then your AB should be equals to BA for every AB belonging to G. So do not forget to write this for every AB. You know why? Because this property may be satisfied for maybe two elements from the set or four elements, but not for everything. So you have to write this for AB belonging to G. Okay. So now how will you prove? So you are already given that AB inverse is A inverse B inverse, and you have to show that AB is equals to BA. Okay, so how do you show? So now you remember one property in a group that we did? We did that element inverse, and then uska wapas se inverse gives you the element back. Now tell me, if A and B are my two elements, then by closure, it's already given to be a group. Hence, by closure, AB exists. So AB is another element now. So now AB is an element, so therefore its inverse also exists. So now you can write AB as AB inverse and then whole inverse, right? So now, remember for groups we did that AB whole inverse is nothing but B inverse A inverse. So that's what we'll do here. So AB inverse will become B inverse A inverse. But we're already given one property. Use this property. What are we given? That AB inverse is A inverse B inverse. So just write here A inverse B inverse and then do whole inverse. Okay. And now use that property. Now see, A inverse B inverse is nothing but some element called C, or C into D inverse. So what will it become? D inverse, C inverse. So now my D here is basically B inverse. So it will become B inverse ka inverse and then A inverse ka inverse. Okay. And this will become B and this will become A. So you are able to prove that AB is equals to BA. Hence the group is abelian. Okay. So this is very simple. All you did was basically this catch, wherein your element was not A or B anymore. It was basically AB. And then you used the property that A inverse ka whole inverse is A. That means any element in the group, if you take twice inverse, you get the element back. So now my element is AB. Okay. And now you'll go for the second part. So second part was when the group is already given to be abelian, you have to prove that AB inverse is A inverse B inverse. Now let's just not move to the solution and try deciphering how will you solve it. You are basically given that the group is abelian and have to show this property that AB inverse is A inverse B inverse. Okay. So how will you show it? Now tell me, start from AB inverse left hand side. Okay. So AB ka inverse, we'll have to prove that this is equals to this. Now instead of AB, can I write instead of AB, can I write BA? Because it's already given that the group is abelian. So it will become BA ka whole inverse. And we know that in a group, C into D whole inverse becomes D inverse C inverse. It reverses the order. So hence, if I'm writing AB as BA, now my A will become first, right? So it will come out to be A inverse B inverse. And that's it. That's the solution. So that's what I did. I basically know that AB is equals to BA. Hence, my AB inverse will be nothing but BA inverse. And then it will be, you expand this, it will become A inverse B inverse. Like that matrix property. Remember? And then this will be hence proved. Okay. So now this is a few. So I'm going to take examples now, extensive, like a lot of examples for the groups. And this is going to go for 2 classes. So please let me know how are you finding these lessons. And I will take up a live class if I have too many doubts. And don't worry, I will be completing group theory at least by, I'm aiming by this month. But it has to be a good, not by this month actually, by month and a half. So it should take that much time. And because there is semigroups also, there's subgroups also, there is like a lot of things like cyclic groups and everything. So I will cover, but it has to be good response from you guys. Otherwise, I'll stop this series because it's taking a lot of time as well. So let me know how do you feel about it. Please comment, subscribe and use that bell icon and spread the word, because modern algebra is something that is not taught by everyone. And I know how much pain it is to be learning this topic and doing it on my own also, and learning from someone else. So do let me know how do you feel about it, and if you want me to continue the series, please comment in the comment box below. Thank you, and meet you in the next video.